On July 12th, 2022, the first deep field image from the James Webb Space Telescope was unveiled to the world. The image showed a patch of sky no larger than a grain of sand held at arm's length. Inside that tiny patch were thousands of galaxies, some so distant that their light had been traveling for more than 13 billion years before reaching Webb's mirrors. Scientists expected the image to confirm decades of work. Instead, it created a problem. Many of those galaxies appeared far larger, brighter, and more developed than they were supposed to be. According to the standard timeline of cosmic evolution, some of them simply should not have existed in the form Webb was seeing them. At first, researchers assumed the data would eventually make sense. Then more observations arrived. Webb found galaxies that seemed to mature far too quickly. It found structures that appeared earlier than models predicted. It strengthened evidence that the universe may be expanding at two different rates simultaneously, and it added new pressure to mysteries that astronomers had been struggling to explain for years. What worries scientists is not any single discovery, it is the pattern. The deeper we look into space, the more often the universe refuses to behave the way our models say it should. Some of the anomalies can probably be explained. Some may disappear with better data, but others have survived repeated observations, independent analyses, and years of scrutiny. And every time one remains, it forces astronomers to confront the same uncomfortable possibility. The map we have been using to understand the cosmos may be missing something important. Quick favor before we continue. If you find yourself coming back to videos like these, hit subscribe so you don't miss the next one. It makes a bigger difference than you might think. Let's begin with the model that was supposed to explain everything, long before the first unexpected galaxies appeared on computer screens. Cosmologists believed they already possessed a remarkably complete story. It was not a guess stitched together from scattered observations. It was a framework built patiently across decades, refined by generations of researchers, and tested against nearly every major astronomical data set available. As we settle into that picture, you can begin to understand why the recent discoveries landed with such force. The framework is known as lambda cold dark matter, usually shortened to lambda CDM. Lambda represents dark energy, the unknown influence driving cosmic expansion to accelerate. Cold dark matter refers to an invisible form of matter that moves relatively slowly and provides much of the gravitational structure shaping the universe. Together, they form the foundation of modern cosmology. Its timeline begins approximately 13.8 billion years ago. At that moment, space itself started expanding from an extraordinarily hot and dense state. Matter, energy, space, and time emerged together. There was no empty void waiting to be filled. Expansion happened everywhere at once. The young universe was intensely energetic. For roughly 380,000 years, light could not travel freely. Photons, the particles of light, collided constantly with charged particles packed throughout space. Imagine trying to see through a storm so dense that every beam is scattered immediately. That was the condition of the cosmos. Gradually, temperatures fell. Electrons joined with protons and formed the first hydrogen atoms. Once those charged particles combined, light finally gained freedom to move across space. That ancient radiation still surrounds us today as the cosmic microwave background, a faint afterglow visible in every direction we look. Then came an era often called the Dark Ages. Hydrogen and helium drifted through expanding space. Gravity worked patiently, gathering matter into denser regions. No stars illuminated the darkness. No galaxies decorated the sky. The ingredients existed, but the structures had not yet emerged. Eventually, the first stars ignited. According to the model, these population 3 stars formed roughly 200 million to 400 million years after the Big Bang. They contained almost no heavy elements, lived brief lives, and burned with tremendous intensity. When they died, their explosions forged new elements and scattered them into surrounding space. Those enriched regions became the birthplace of future generations of stars. Small proto-galaxies began appearing, irregular, primitive, modest in scale. Time did the rest. Over billions of years, gravity assembled larger systems from smaller ones. Galaxies merged, structures matured, spiral arms formed, clusters emerged. The familiar cosmic architecture of the modern universe slowly took shape, and the evidence seemed overwhelming. Satellite missions mapped the cosmic microwave background with astonishing precision. Supernova surveys measured cosmic expansion. Redshift maps traced the distribution of galaxies across immense distances. Again and again, Lambda CDM survived scrutiny. That success shaped expectations. The James Webb Space Telescope was never intended to overthrow this model. Its mission was far more modest. Researchers expected sharper details, earlier snapshots, and a clearer view of processes already understood. But when Webb opened its mirror to the distant universe, the details refused to behave as expected. Astronomers often describe distance as a form of time travel. The farther outward we look, the farther backward we see. A galaxy observed across 13 billion light years appears not as it is today, but as it existed when that light first began its journey. With the James Webb Space Telescope reaching deeper than any observatory before it, researchers expected to witness the universe in its earliest stages of assembly. Instead, they found cities where villages should have been. Among the most striking discoveries is a galaxy known as Jade's GSZ 140, confirmed during 2024. Its light comes from a time only about 290 million years after the Big Bang, that places it astonishingly close to the beginning of cosmic history. Yet nothing about it appears primitive. Observations indicate hundreds of millions of stars already shining within it. New stars continue forming at a vigorous pace. Dust and heavier elements are present as well, materials that require earlier generations of stars to live, die, and enrich their surroundings before later generations can emerge. That sequence takes time. According to conventional expectations, the universe at this age should still have been constructing its first modest stellar systems. Gas clouds were supposed to be gathering. Small structures were expected to dominate. Large, mature galaxies belonged much later in the timeline. But Jade's GSZ 140 arrived early. The challenge extends beyond a single object. Several distant galaxies observed by Webb display similar characteristics. They appear brighter, heavier, and more developed than theoretical models anticipated. Some seem to have assembled enormous stellar populations with remarkable speed. Researchers began comparing calculations. The numbers refused to cooperate. To create galaxies of this scale, so soon after cosmic dawn, requires vast reservoirs of matter and efficient star formation processes. Simulations based on lambda cold dark matter struggle to produce such outcomes within the available time. The required growth rates push against limits that had long seemed reasonable. This tension attracted attention throughout the field. Astronomer Evo Lab and colleagues examined a collection of unexpectedly massive early galaxies and described them in a Nature paper using a phrase that spread rapidly through astronomy. They called them universe breakers. The wording carried weight. Scientific papers are usually cautious documents. Researchers tend to avoid dramatic language, yet these objects appeared significant enough to justify terminology that reflected genuine concern. Statistics deepened the issue. Standard predictions suggested galaxies this massive should be extraordinarily rare at such early epochs. Webb's observations indicated they may be 10 to 100 times more common than expected. A difference of that scale reaches beyond ordinary uncertainty. Independent teams checked the results. Different methods produced similar conclusions. Alternative analyses, separate data sets, and repeated observations continued pointing in the same direction. Instrument failure became increasingly difficult to invoke. Simple computational mistakes offered little comfort. Several explanations remain under investigation. Perhaps early star formation operated with an efficiency never captured in previous simulations. Perhaps unseen dark matter structures accelerated growth from the beginning. Perhaps portions of cosmic history unfolded differently than current timelines suggest. None of those possibilities has earned consensus. Yet each asks us to reconsider assumptions that once seemed secure, and the galaxies continue shining exactly where the model expected, almost none at all. Sometimes the challenge arrives from the edge of the observable cosmos. Sometimes it waits almost in our own celestial neighborhood. Just 190 light years from Earth, a single star has spent decades forcing astronomers into an uncomfortable conversation about time itself. Its catalog designation is HD 140283. Most people know it by another name, the Methuselah star. This ancient object moves through the halo of the Milky Way, a vast spherical region surrounding our galaxy. Halo stars are often extremely old, formed when the universe was still young and heavy elements remained scarce. Astronomers expected Methuselah to be ancient. They did not expect impossible. Early measurements suggested an age of roughly 16 billion years. That immediately created a problem. The universe itself is estimated to be 13.8 billion years old. A star cannot logically predate the universe that produced it. Yet the calculations kept returning troubling values. These estimates were not casual guesses. Researchers used some of the most sophisticated stellar dating methods available. A star's spectrum, the pattern of light spread into different wavelengths, contains chemical clues about its history. By examining the abundance of certain elements and comparing them with detailed models of stellar evolution, astronomers can estimate how long a star has existed. The process is painstaking. Observations from the Hubble Space Telescope improved distance measurements. Refined stellar physics updated assumptions about energy production deep inside stars. Researchers recalculated again and again. The age decreased, but only slightly. The revised estimate settled near 14.46 billion years. That value carries uncertainties large enough to overlap with the accepted age of the universe. Yet the overlap remains uncomfortably narrow. The tension never fully disappeared. The International Astronomical Union acknowledged the discrepancy. No definitive resolution followed. For many years, the Methuselah star remained a peculiar exception, an oddity filed away in the margins of cosmology. But recent observations have complicated that interpretation. As Webb examined increasingly distant galaxies, astronomers began finding stellar populations whose chemical characteristics hinted at unexpectedly mature histories. These stars are not individually dated with the same precision as Methuselah. Even so, their elemental fingerprints suggest that stellar evolution may have progressed remarkably quickly in the earliest epochs of cosmic history. The available timeline grows compressed. Processes once thought to require lengthy periods may have unfolded faster than expected. That possibility remains under active investigation. Alternative explanations exist as well. Perhaps our measurement of the universe's age requires revision. Perhaps stellar dating contains a subtle systematic error that researchers have yet to identify. Another possibility suggests that the earliest generations of stars formed through pathways not fully represented in current models. Each option carries consequences. A change to cosmic age would affect nearly every branch of cosmology. Hidden flaws in stellar dating would require re-evaluating countless observations. New mechanisms of early star formation would reshape our understanding of how structure emerged after the Big Bang. Meanwhile, the Methuselah star continues its journey through space, close by in cosmic terms, still shining, still measured, still resisting easy explanation, and after decades of scrutiny, it remains one of astronomy's most persistent reminders that even nearby stars can challenge the deepest assumptions about the universe. Imagine standing between two perfectly calibrated clocks. Both are built by experts, both have been checked repeatedly, both appear trustworthy, yet every day they disagree by the same amount. That is the situation cosmologists now face when they attempt to measure the expansion of the universe. The expansion itself is not in doubt. Galaxies drift apart as space stretches between them. The farther a galaxy lies from us, the faster it appears to recede. This relationship is described by the Hubble constant, a number that tells us how quickly cosmic expansion is occurring across vast distances. For decades, researchers worked to refine that number. The challenge seemed straightforward: measure carefully enough, reduce uncertainties, and eventually every method should converge on the same answer. Instead, the opposite happened. One approach begins with the cosmic microwave background, the ancient radiation released when the young universe first became transparent. Using observations from the Planck satellite, scientists can reconstruct the conditions of the early cosmos and calculate how fast expansion should be occurring today. The result is precise. Planck produces a value of roughly 67.4 kilometers per second for every megaparsec of distance. A megaparsec is a cosmic measuring stick equal to about 3.26 million light years. A completely different method starts much closer to home. Astronomers use Cepheid variable stars, pulsating stars whose changing brightness reveals their true luminosity. By comparing actual brightness with observed brightness, distances can be calculated. Those measurements calibrate Type 1a supernovae, stellar explosions bright enough to be seen across immense reaches of space. That technique tells another story. Repeated observations consistently produce a value near 73 kilometers per second per megaparsec. The difference may sound modest, yet in precision cosmology, it is enormous. This discrepancy has a name: the Hubble tension. For more than a decade, researchers expected the disagreement to fade as better instruments arrived. Many suspected hidden errors within the local distance ladder. Nearby stars might contaminate observations. Distances could be subtly miscalculated. Small corrections seemed likely. Then Webb joined the investigation. Its infrared instruments examined Cepheid variables with unprecedented clarity, cutting through effects that had complicated earlier measurements. If the local method contained a major flaw, Webb had an excellent chance of finding it. But the flaw never appeared. The new measurements reinforced the previous ones. The local expansion rate remained stubbornly high. Instead of narrowing, the gap became harder to dismiss. That changed the discussion. When two independent techniques produce incompatible answers despite increasing precision, attention naturally shifts away from measurement error. Researchers begin wondering whether some piece of physics is absent from the model itself. Several possibilities have emerged. One proposal involves early dark energy, an additional burst of energy that briefly influenced expansion during the universe's infancy. Another suggests unknown particles may have existed before recombination, the era when electrons and protons first combined into atoms. Neither explanation has secured confirmation. Meanwhile, the disagreement persists. Every improvement in accuracy strengthens the reality of the tension, and with each passing year, the universe continues presenting two expansion rates where only one should exist. If cosmologists could choose a single image to preserve from all of modern astronomy, many would select a map that contains no stars, no galaxies, and no planets. It appears at first glance as a mottled pattern of colors spread across the sky. Yet hidden within that pattern is a record from when the universe was only 380,000 years old. This is the cosmic microwave background. It is often described as the oldest light we can observe. More importantly, it serves as a snapshot of the young cosmos before galaxies existed. The European Space Agency's Planck satellite measured this radiation with extraordinary precision, creating one of the most successful datasets in scientific history. By most standards, it behaves beautifully. The tiny temperature variations scattered across the map match the predictions of lambda cold dark matter remarkably well. These minute fluctuations, warmer here and cooler there by tiny fractions of a degree, acted as the seeds from which all future cosmic structure eventually emerged. The overall fit is impressive, yet perfection remains elusive. Buried inside this otherwise elegant picture are several features that refuse to sit comfortably within the model. Each one is small compared with the entire dataset. Each one can be argued away individually. Together, they continue attracting attention. One example is known as the cold spot. This region appears noticeably cooler than surrounding areas and spans an enormous section of the sky. When translated into physical scale, it corresponds to roughly 1.8 billion light-years across. Researchers proposed that a supervoid, an immense region containing fewer galaxies than expected, might explain the effect. The idea seemed promising, but detailed surveys revealed a void that appears insufficient. The observed deficit in galaxies does not fully account for the temperature difference. Another puzzle emerges when the sky is divided into hemispheres. One half exhibits slightly more temperature variation than the other. The imbalance is subtle, yet statistically significant enough to persist through repeated analyses. According to the standard model, the universe should display the same large-scale properties in every direction. This asymmetry complicates that expectation. A third anomaly concerns the largest patterns visible in the cosmic microwave background. These patterns are known as the quadrupole and octupole. Those names simply describe large-scale temperature structures extending across enormous portions of the sky. What caught attention was their alignment. Rather than pointing in unrelated directions, they appear correlated. The coincidence is unusual enough that cosmologists informally labeled it the axis of evil, a memorable name reflecting genuine discomfort rather than formal theory. None of these observations alone overturns cosmology. Statistical fluctuations remain possible. Large datasets occasionally produce strange patterns by chance. Yet these features have survived different analysis techniques, different processing methods, and repeated scrutiny over many years. That persistence matters. Webb cannot observe the cosmic microwave background directly. Its instruments operate in a very different realm. But as increasingly early galaxies reveal structures forming sooner than expected, some researchers have begun revisiting these older anomalies through a new lens. The possibility remains open that what once appeared to be isolated irregularities may represent faint traces of physical processes that current models have yet to fully capture. Take a step back from individual galaxies for a moment. Imagine rising far beyond clusters, beyond superclusters, until entire regions of the cosmos become visible at once. From that perspective, the universe does not resemble a random scattering of lights. It resembles a network, a vast one. Astronomers call it the cosmic web. This immense framework consists of filaments, long strands of galaxies stretching across space, connected at dense intersections and separated by enormous voids containing relatively little matter. Over decades, galaxy surveys confirmed that the large scale universe follows this pattern remarkably well. The prediction was successful. According to lambda, cold dark matter, gravity gradually shaped this structure over billions of years. Small density fluctuations grew larger, matter accumulated, filaments emerged. The web slowly developed into the arrangement we observe today. Yet, scale introduces a problem. Some structures appear so large that known cosmic history struggles to accommodate them. They are not merely bigger than average, they approach dimensions that challenge assumptions about how quickly matter can organize itself. One of the most striking examples is the Hercules Corona Borealis Great Wall. Its estimated length reaches roughly 10 billion light years. To appreciate that figure, consider that the observable universe spans about 93 billion light years across. A structure measuring 10 billion light years is not a minor feature hidden in some distant corner. It occupies a substantial fraction of the observable cosmos itself. That creates tension. Gravity works continuously, but it works at finite rates. Matter requires time to gather into coherent patterns. Standard models suggest there simply has not been enough cosmic history available for something this enormous to emerge naturally. Another challenge arrived during 2021. Researchers identified a structure called the Giant Arc. Stretching approximately 3.3 billion light years, it appears as a vast curved arrangement of galaxies spanning a huge section of the sky. Its size is problematic. Cosmology includes a benchmark known as the Baryon Acoustic Oscillation Scale. This scale traces ancient sound waves that moved through the young universe before atoms formed. The resulting pattern establishes a characteristic upper size for coherent structures, roughly 1.2 billion light years. The giant arc exceeds that comfortably, yet it exists. Observations continue revealing additional examples that approach or surpass expected limits. Each discovery adds another piece to a growing puzzle concerning how matter organizes itself across the largest distances. Webb contributes a different perspective. Rather than focusing primarily on nearby large-scale structures, it peers deep into earlier epochs. There, researchers have found evidence that organized filamentary arrangements may have appeared sooner than simulations predicted. Instead of developing gradually over extended periods, aspects of the cosmic web seem to emerge surprisingly early. That possibility carries implications. If large-scale organization began earlier than expected, some oversized structures may become easier to explain, but current models have not fully bridged the gap. Survey after survey continues expanding the catalog of immense formations, while theoretical explanations remain incomplete. For now, the universe appears more interconnected, more organized, and perhaps far older in its architecture than our simulations anticipated. Some mysteries emerge from objects that are missing. Others emerge from objects that seem to have arrived far too early. Among the most striking examples are black holes that appear fully grown during an era when the universe should still have been in its cosmic infancy. Nearly every large galaxy we observe today contains a supermassive black hole at its center. These are gravitational giants containing millions or even billions of times the mass of our Sunday. The Milky Way hosts one of its own, Sagittarius A star, with a mass of roughly 4 million suns. By cosmic standards, that is modest. The challenge begins when we look deep into the past. Webb has revealed galaxies that existed less than 700 million years after the Big Bang, yet some already contain central black holes weighing hundreds of millions or even billions of solar masses. That should be difficult. Black holes do not simply appear at enormous sizes. Under conventional models, they begin as the remnants of massive stars. From there, they grow by pulling in surrounding gas, dust, and stars. The process is powerful, but it is not unlimited. Physics imposes a speed limit. Astronomers call it the Eddington limit. This threshold describes the point where radiation produced by infalling matter becomes strong enough to push additional material away. In simple terms, a black hole cannot feed infinitely fast because its own energy output starts interfering with the process. Growth becomes regulated. When researchers calculate how rapidly black holes should gain mass under this constraint, a troubling result appears. Even beginning very early and feeding continuously at the maximum allowed rate, many of Webb's observed black holes still seem too massive for the time available. The arithmetic falls short. This discrepancy is known as the early black hole problem. Previous observatories hinted at it. Webb has intensified it by uncovering more examples and pushing observations closer to the beginning of cosmic history. Several explanations compete for attention. One possibility proposes that some black holes never formed from ordinary stars at all. Instead, vast clouds of gas may have collapsed directly into massive black holes, bypassing intermediate stages entirely. These hypothetical objects are known as direct collapse black holes. Another idea reaches even deeper. Some researchers investigate primordial black holes, exotic objects that may have formed during the first moments after the Big Bang itself. If such objects existed, they could provide massive seeds that later growth would enlarge. There is another route. Perhaps the Eddington limit was occasionally exceeded. Short periods of extremely rapid feeding, known as super Eddington accretion, might allow black holes to gain mass faster than standard calculations assume. Webb has added another complication. Scattered throughout deep field images are objects informally called little red dots. These compact red sources appear surprisingly numerous. Many seem to represent intensely active black holes embedded within young galaxies. Their abundance is unexpected. Each detection adds pressure to existing formation models. The observations themselves are increasingly secure. The black holes are there. Their host galaxies are there. Their immense masses are there. What remains uncertain is the pathway that produced them. The deeper Webb looks, the more these ancient gravitational giants appear less like exceptions and more like a fundamental clue that something important is still missing from the story. For most of human history, the radio sky seemed relatively familiar. Pulsars flashed with dependable rhythms. Galaxies emitted steady signals. Even exotic objects generally followed patterns that astronomers could study over time. Then researchers stumbled upon something that lasted less than the blink of an eye and changed the field. In 2007, astronomer Duncan Lorimer and his team examined archival observations collected during 2001. Hidden within the data was a brief burst of radio energy unlike anything previously documented. It lasted less than a millisecond and then vanished. At first, skepticism followed. A signal so short and so powerful seemed suspicious. Some wondered whether it originated from Earth rather than deep space, but additional detections soon appeared. The strange pulse was real, and it was arriving from far beyond our galaxy. Astronomers gave it a name: fast radio burst. An individual burst releases an astonishing amount of energy. In less than a thousandth of a second, an FRB can emit as much energy as our sun produces across several days. That energy is concentrated into a narrow radio beam capable of crossing billions of light years before reaching Earth. For years, nobody knew the source. Ideas multiplied rapidly. Colliding neutron stars entered the discussion. Evaporating black holes were considered. Some researchers explored highly speculative possibilities involving extraterrestrial technology. The mystery remained open because observations provided very little information beyond the bursts themselves. Then came a breakthrough. During 2020, astronomers detected a fast radio burst originating inside the Milky Way. The source was traced to a magnetar, a type of neutron star possessing an extraordinarily powerful magnetic field. The discovery confirmed that magnetars can generate FRBs. A major clue emerged, but the puzzle survived. Many bursts fit comfortably within magnetar models, others do not. Some repeat hundreds of times. Certain bursts arrive in intricate sequences, displaying frequency drifts and internal structures that remain difficult to reproduce theoretically. One source became especially famous: Fast Radio Burst 2012 1102. A originates from a dwarf galaxy approximately 3 billion light years away. It has produced hundreds of detected bursts. Activity arrives in clusters separated by inactive periods, suggesting some recurring process may be involved. The pattern raises questions. Meanwhile, researchers discovered that FRBs are valuable for reasons extending beyond their origin. Every burst travels through vast regions of intergalactic space before reaching Earth. Along the way, diffuse matter slightly delays lower radio frequencies compared with higher ones. This effect contains information. Scientists call the technique dispersion measure analysis. In plain terms, it allows astronomers to estimate how much matter exists between a burst and our telescopes. No other tool can probe these immense stretches of nearly invisible material with comparable efficiency. The results proved transformative. During 2020, FRB observations helped locate the universe's missing baryons, the ordinary matter predicted by cosmological theory, but frustratingly difficult to detect directly. Researchers found much of it spread through tenuous filaments connecting galaxies across the cosmic web. The bursts continue arriving. Their energies are measurable. Their distances are measurable. Their repeating behaviors are measurable. Yet despite hundreds of detections and increasingly sophisticated observations, the complete explanation remains unfinished, carried across the universe in flashes that last less than a heartbeat. For centuries, every astronomical discovery arrived through some form of light. Visible light revealed planets. Radio waves uncovered pulsars. Infrared detectors exposed hidden galaxies. No matter the wavelength, we learned about the universe by collecting radiation that traveled across space. Then, in September of 2015, something entirely different arrived. It was not light. The signal lasted less than a second. Deep beneath the noise of Earth's environment, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, recorded a tiny distortion passing through the planet. Two black holes located roughly 1.3 billion light years away had collided and merged into a single object. Space itself had trembled. The effect was astonishingly small. LIGO's 4-kilometer detector arms changed length by less than 1,000th of a proton's diameter. Yet the measurement was clear enough to confirm a prediction Albert Einstein had made a century earlier. Astronomy changed overnight. For the first time, researchers were not observing matter through emitted radiation. They were observing changes in space-time itself, the underlying geometry of the universe. More detections followed. LIGO was joined by Virgo in Europe and CAGRA in Japan. Together, they recorded dozens of gravitational wave events. Most involved merging black holes. Others came from neutron stars. A few proved difficult to categorize using existing expectations. The catalog continued growing, but a second development emerged during 2023 that may prove equally significant. Several international collaborations announced evidence for something called a gravitational wave background. Unlike a single merger event, this signal does not arrive as a brief pulse. It resembles a persistent cosmic vibration spread throughout space. Detecting it required a very different method. Researchers turned to pulsars, rapidly spinning neutron stars that emit radio pulses with extraordinary regularity. They function like clocks. Some rotate hundreds of times every second while maintaining astonishing precision. By monitoring dozens of these objects across the galaxy, astronomers can search for tiny synchronized timing shifts. Those shifts reveal gravitational waves passing between Earth and the pulsars. The results were intriguing. A background signal had long been predicted. Most models expected it to arise from countless pairs of supermassive black holes orbiting and merging throughout cosmic history. Yet the detected signal appears stronger and somewhat different from standard forecasts. That difference matters. One possibility suggests contributions from primordial gravitational waves. These hypothetical waves would have originated during the earliest fractions of a second after the Big Bang, long before atoms existed and long before the universe became transparent. Such a discovery would be extraordinary. Light cannot show us conditions before the cosmic microwave background formed. Gravitational waves can travel directly from those remote epochs, carrying information from a time otherwise hidden from observation. Meanwhile, gravitational wave astronomy has already transformed our understanding of heavy elements. During 2017, researchers observed an event known as GW 170817. Two neutron stars collided, producing both gravitational waves and electromagnetic signals observed by 17 separate telescopes. The aftermath revealed a cosmic forge. Elements such as gold, platinum, and uranium are created in these violent mergers. The gold in a wedding ring, the uranium inside Earth's crust, and countless heavy atoms surrounding us today began their existence in collisions between dead stars long before our sun was born. There are places in the universe where familiar matter reaches its limits. Atoms cease behaving as they do on Earth. The distinction between particles begins to blur. Physical laws remain intact, yet they are pushed into conditions so extreme that even our best theories struggle to keep pace. Neutron stars occupy that territory. They form when a massive star exhausts its nuclear fuel and explodes as a supernova. If the remaining core contains roughly between 1.4 and 3 solar masses, gravity overwhelms ordinary matter. The collapse continues until the core becomes a neutron star rather than a black hole. The result is extraordinary. More mass than our sun becomes compressed into a sphere only about 20 kilometers across, roughly comparable to the size of a medium city. The density is almost impossible to visualize using everyday experience. Atoms cannot survive there. Under immense pressure, electrons and protons are forced together, producing neutrons. What remains is an object composed primarily of tightly packed neutrons, held up by a quantum mechanical effect called neutron degeneracy pressure. In simple terms, quantum physics prevents identical neutrons from occupying exactly the same state. That resistance holds gravity back for a time. A teaspoon of neutron star material would weigh approximately 10 million tons on Earth, yet even that astonishing density may not represent the final stage of compression occurring inside these objects. The deepest layers remain mysterious. At the center, pressures may become so intense that neutrons themselves begin to break apart. Their constituent particles, known as quarks, could be released into an exotic state called quark-gluon plasma. This form of matter existed briefly during the first moments after the Big Bang. Perhaps it still exists today. If such cores are real, some neutron stars may actually contain strange quark matter, a hypothetical phase unlike anything directly observed. No laboratory on Earth can reproduce these conditions for more than fleeting fractions of a second. Nature performs the experiment for us. Recent gravitational wave observations have provided new clues. When neutron stars collide, they generate ripples in spacetime, carrying information about their internal structure. Physicists analyze these signals using something called the equation of state, a description of how matter responds to changing pressure and density. The details matter greatly. Data from the famous merger event, GW 170-817 and later, detections have narrowed estimates of neutron star sizes and internal properties. Yet the results do not align perfectly with all theoretical predictions. Complexity remains. Some models predict matter should behave more rigidly. Others suggest greater compressibility. Observations continue eliminating possibilities while revealing new uncertainties about what truly exists inside these stellar remnants. Certain neutron stars introduce another layer of strangeness. These are magnetars, objects possessing magnetic fields approximately 1 trillion times stronger than Earth's. Their crusts occasionally crack under internal stress, releasing immense bursts of energy known as starquakes. The effects can travel astonishing distances. In 2004, the most powerful magnetar flare ever recorded originated about 50,000 light years away. Despite that distance, the event briefly altered Earth's upper atmosphere. We often think of matter as familiar and predictable. Neutron stars suggest otherwise. They reveal that under sufficient pressure, nature enters regimes where matter itself becomes something almost unrecognizable, existing at the boundary between established physics and the unknown. Most discoveries discussed in astronomy involve enormous distances and ancient events. They reshape our understanding of physics, structure, and cosmic history. Yet occasionally, a dataset arrives carrying a more personal implication. It raises a question that people have asked long before telescopes existed. Could life exist elsewhere? One of the most closely watched candidates is a planet called K2-18b. It orbits a small red dwarf star located approximately 124 light-years from Earth. With a mass about 8.6 times greater than our planet, it occupies what astronomers call the habitable zone, the region around a star where temperatures may allow liquid water to exist. That placement alone attracts attention, but Webb's observations added something more. During 2023, the telescope examined K2-18b using a method known as transmission spectroscopy. When a planet passes in front of its star, a small fraction of starlight filters through the planet's atmosphere before reaching us. Different molecules absorb different wavelengths of light, leaving distinctive signatures embedded within that spectrum. The atmosphere reveals itself. Analysis confirmed the presence of methane and carbon dioxide. Both molecules are important because they help researchers reconstruct atmospheric chemistry. Together, they support the possibility that K2-18b belongs to a proposed class of worlds called Hycean planets. The term combines hydrogen and ocean. These hypothetical planets possess hydrogen rich atmospheres above vast liquid water environments. If such worlds exist, they could dramatically expand the number of potentially habitable environments throughout the galaxy. Then another signal appeared. Researchers reported tentative evidence for dimethyl sulfide. On Earth, this molecule is produced predominantly by marine microorganisms, particularly phytoplankton living within the oceans. The announcement drew immediate interest. No claim of life was made. The signal reached only about 1 to 2 sigma statistical significance, a measure of confidence that falls well below the threshold required for scientific confirmation. Random fluctuations remain entirely possible. Even so, context matters. A potentially habitable planet, an atmosphere containing methane and carbon dioxide, and a possible biosignature molecule appearing within the same dataset created a combination difficult to ignore. Researchers responded carefully. The team emphasized uncertainty. Further observations were requested. Alternative chemical explanations remain under investigation. Every effort has focused on verification rather than excitement. K218b is only part of a larger effort. Webb has also begun examining the famous TRAPPIST-1 system, located roughly 40 light-years away. 7 rocky planets orbit its small red dwarf star. Several reside within the habitable zone and rank among the most promising nearby targets for atmospheric studies. Results have been mixed. Some worlds appear to lack substantial atmospheres. Others remain under active investigation. Observations continue accumulating, spectrum by spectrum, molecule by molecule. That slow process is important. Extraordinary conclusions demand extraordinary evidence. Astronomers understand the stakes involved. Yet the reason this dataset continues drawing attention is simple. For the first time in human history, we possess instruments capable of detecting possible biological chemistry on planets orbiting distant stars. The signal from K2-18b remains uncertain. The atmosphere remains under study. But somewhere across 124 light-years of space, a world has given us enough evidence to keep looking closely, and that alone marks a remarkable moment in the history of science. Some of the most compelling places in the search for life do not orbit distant stars at all. They circle familiar planets that have shared our night sky for centuries. While attention often turns toward remote worlds beyond the solar system, there are destinations much closer that continue to grow more intriguing with every observation. Europa is one of them. As the fourth largest moon of Jupiter, Europa appears at first glance to be a frozen sphere wrapped in fractured ice. Long reddish streaks crisscross its surface. Vast cracks run for thousands of kilometers. Beneath that frozen exterior, however, scientists believe an immense ocean is hidden from view. The scale is astonishing. Current estimates suggest Europa's subsurface ocean contains between 2 and 3 times as much water as all of Earth's oceans combined. That water remains liquid because Jupiter constantly flexes the moon through gravity. During each orbit, Europa is stretched and compressed, generating internal heat deep below the ice. A frozen surface hides a dynamic interior. For decades, researchers suspected communication existed between the ocean below and the crust above. Then observations from the James Webb Space Telescope provided important support. During 2023, Webb detected carbon dioxide concentrated in a region known as Terra Regio. Analysis suggested the carbon likely originated from the hidden ocean rather than arriving through impacts from space. That distinction matters. Carbon dissolved in liquid water and interacting with a rocky seafloor creates conditions that many scientists consider favorable for biology. On Earth, water, carbon, and active geology form a powerful combination, but Europa may not be the most remarkable example. Farther from the Sun, orbiting Saturn, lies Enceladus. Compared with Europa, it is a relatively small moon, yet it performs something extraordinary. Instead of keeping its ocean concealed, Enceladus ejects part of it directly into space. From fractures near the South Pole, towering geysers spray water vapor and ice particles hundreds of kilometers outward. These plumes are so extensive that they help replenish Saturn's E ring, one of the planet's broad outer rings. We have sampled that ocean already. Between 2005 and 2017, NASA's Cassini spacecraft repeatedly flew through the plumes. Instruments detected water vapor, complex organic compounds, molecular hydrogen, and tiny silica particles. Molecular hydrogen is especially important because it suggests chemical reactions between water and hot rock on the ocean floor. Those reactions resemble hydrothermal systems on Earth. Along our own ocean floor, hydrothermal vents support entire ecosystems without sunlight. Microorganisms draw energy from chemistry rather than solar radiation. Around those microbes, complex communities thrive in complete darkness. The parallels are difficult to ignore. Interest in Europa has therefore intensified. In October 2024, NASA launched the Europa Clipper mission. After a journey lasting several years, the spacecraft is expected to arrive in Jupiter's system during 2030. It will perform 49 close flybys, measuring ice thickness, ocean properties, surface chemistry, and indicators of habitability. What makes these missions remarkable is their focus. Researchers are no longer asking whether these oceans exist. Evidence strongly suggests they do. The goal now is determining whether environments beneath those frozen shells possess the ingredients necessary for life, making two icy moons among the most compelling destinations in modern planetary science. Consider a simple difference in timing. The universe is approximately 13.8 billion years old. Earth formed around 4.5 billion years ago. Between those two dates lies an immense span of cosmic history, enough time for entire civilizations to rise and vanish long before our planet existed. The arithmetic becomes difficult to ignore. If life emerged elsewhere even a few 100 million years before it appeared here, another species could possess an almost unimaginable head start. Stretch that advantage to 1 billion years, and the gap becomes vast beyond ordinary comprehension. Civilizations do not need impossible technology. Even traveling at a small fraction of light speed, a society with millions of years available could spread gradually from star to star. Given enough time, the entire Milky Way could be explored, settled, or transformed many times over. Yet when we look outward, we find no confirmed evidence. This contradiction sits at the heart of a problem proposed by physicist Enrico Fermi in the 1950s. If intelligent life should be common, where is everybody? The question has only grown sharper. Observations over the last 2 decades have transformed our understanding of planets. Before the Kepler mission, many astronomers suspected planetary systems might be unusual. Instead, Kepler revealed that planets are abundant throughout the galaxy. They appear almost everywhere we look. Data from Kepler and the Transiting Exoplanet Survey satellite, often shortened to TESS, suggests roughly 1 in 5 Sun-like stars hosts an Earth-sized planet within its habitable zone. That estimate translates into tens of billions of potentially suitable worlds in the Milky Way alone. Then there is chemistry. Complex organic molecules have been detected inside interstellar clouds drifting between stars. Similar compounds appear in meteorites that reach Earth. Atmospheric studies of distant planets continue revealing ingredients associated with biological processes. The raw materials seem widespread. Recent observations from the James Webb Space Telescope strengthen that picture. Rocky planets are common. Planetary diversity is enormous. Habitable environments may be far less rare than earlier generations imagined, but the sky remains absent of clear technological signatures. No confirmed artificial radio transmissions have been verified. No engineered structures spanning solar systems have been observed. No unmistakable evidence of galaxy scale construction projects has appeared. The discrepancy grows. One proposed explanation is called the Great Filter. This hypothesis suggests a difficult barrier exists somewhere between simple chemistry and advanced civilization. Perhaps the obstacle lies behind us, making intelligent life extraordinarily rare. Perhaps it appears later, preventing most technological species from surviving long enough to expand among the stars. The second possibility carries obvious implications. It suggests civilizations routinely encounter challenges they fail to overcome. Environmental collapse, technological accidents, conflict, or unknown factors could halt expansion before it truly begins. No answer has been confirmed. That uncertainty is what gives the paradox its persistence. Every year, our catalog of potentially habitable worlds expands. Every year, the conditions favorable to life appear more common. Yet every year, the absence of a clear response becomes harder to dismiss. The universe increasingly resembles a place where life should emerge often. The enduring mystery is why, despite all those opportunities, we have yet to find unmistakable evidence that anyone else has answered back. Imagine drifting between the stars, with no sunrise, no sunset, and no parent star lighting the sky. Across the galaxy, countless worlds may spend their entire existence in that state, moving through interstellar space alone. Astronomers call them rogue planets. Unlike Earth, Jupiter, or any of the familiar planets in our solar system, rogue planets are not bound to a star. Most are thought to begin life within ordinary planetary systems before gravitational chaos changes their fate. During the turbulent early stages of planet formation, close encounters between giant worlds can act like cosmic slingshots. Some planets are thrown away forever. A sufficiently powerful gravitational interaction can accelerate a world beyond escape velocity, sending it into the darkness between stars. Once expelled, it becomes a free-floating planet, carrying only its own heat and momentum across the galaxy. For many years, these objects remained largely theoretical. They emit virtually no visible light. Detecting them is extraordinarily difficult. But the James Webb Space Telescope observes the universe in infrared wavelengths, making it sensitive to faint heat signatures that invisible worlds still radiate long after their formation. That capability has opened a new frontier. In 2023, Webb examined the Orion Nebula, one of the nearest active star forming regions. Among the young objects scattered throughout the cloud, researchers identified roughly 40 rogue planets with masses comparable to Jupiter. Then came a surprise. Many of these worlds appeared to exist in pairs. Rather than wandering alone, they traveled together while remaining gravitationally bound to one another. Researchers named them Jupiter mass binary objects, commonly shortened to jumbos. The discovery created immediate problems. Standard planetary formation models do not naturally predict such systems. Planets forming around stars may occasionally be ejected, but producing two massive planets that remain bound together during that violent process is difficult to explain. Current simulations struggle with it. An alternative possibility has therefore gained attention. Perhaps some jumbos never formed inside planetary systems at all. Instead, they may have originated directly from collapsing clouds of gas and dust, following a process more similar to star formation. That blurs familiar categories. If an object forms like a star but lacks sufficient mass to ignite nuclear fusion, is it truly a planet? Or is it something occupying the boundary between planetary and stellar evolution? The questions continue. Even more intriguing are the implications for habitability. Without a nearby star, a rogue planet seems immediately hostile. Yet some theoretical studies suggest otherwise. Internal heat generated by radioactive decay could persist for billions of years. A thick hydrogen atmosphere might act as insulation, trapping warmth near the surface. Liquid water could survive, perhaps beneath an icy crust, perhaps within subsurface oceans, in some scenarios, potentially for immense spans of time. Estimates now suggest the Milky Way may contain hundreds of billions of rogue planets, possibly exceeding the number of stars themselves. They drift through interstellar darkness without belonging to any solar system, forming a hidden population that remained largely invisible until recently. We are only beginning to find them, and already they are challenging assumptions about what a planet can be. Astronomers sometimes learn as much from an absence as from a discovery. A missing signal can become just as important as a detected one. In some cases, the thing we expected to find ends up revealing more by refusing to appear. That is the situation with population. 3 stars. According to the standard cosmological timeline, these were the first stars ever born. They emerged between roughly 100 million and 400 million years after the Big Bang, during an era when the universe contained almost nothing except hydrogen and helium. No heavier elements existed yet. Carbon had not formed. Oxygen did not exist. Iron had not been created. The raw ingredients that would eventually build planets, oceans, and living organisms had not entered cosmic history. The first stars changed that. Because their gas clouds lacked heavier elements that help cool collapsing matter, theoretical models suggest population. 3 stars grew extraordinarily massive. Some may have reached hundreds of times the sun's mass. They lived fast. Enormous stars consume their fuel rapidly. Instead of surviving billions of years, many likely existed for only a few million years before ending their lives in violent explosions. Those explosions transformed everything. Inside their cores, nuclear fusion forged the first heavy elements. When the stars died, those materials spread into surrounding space. Every later generation of stars inherited that enriched gas. The atoms within your body trace their ancestry back to those ancient stellar furnaces. Finding direct evidence of them became a major goal. The James Webb Space Telescope was designed partly to observe the earliest galaxies ever formed. Many researchers hoped it might finally reveal population 3 stars themselves, or at least unmistakable chemical signatures left behind by their presence. But the search has produced an unexpected result. The earliest galaxies observed by Webb already contain heavy elements. Their gas is not pristine. Chemical enrichment had already occurred before the telescope captured those systems. Something happened earlier. The implication is that population 3 stars formed, evolved, and disappeared with remarkable speed. By the time the earliest currently observable galaxies emerged, the first generation had already altered the surrounding universe. The timeline becomes compressed. Galaxies that already appeared surprisingly mature now seem to have inherited material from stellar ancestors that may have completed their entire life cycles even sooner than many models predicted. Researchers continue searching. In 2023, one study reported a possible indirect signature of population, 3 stars within a highly magnified galaxy, observed through gravitational lensing, a phenomenon where gravity bends and amplifies distant light. The interpretation remains under active debate. No consensus exists yet, but the absence itself has become valuable data. Webb's extraordinary sensitivity places limits on what population 3 stars could have been. If they remain undetected, perhaps they were rarer than expected. Perhaps they burned out more quickly. Perhaps they formed through processes that differ from current assumptions. The first stars illuminated the universe and helped end the cosmic dark ages. Their radiation transformed surrounding hydrogen and allowed light to travel more freely through space. Their influence appears everywhere. Their presence is written across the cosmos. Yet the stars themselves remain hidden, known primarily through the traces they left behind, like the earliest chapter of a story whose opening pages have vanished while the consequences continue unfolding billions of years later. There is a strange situation at the heart of modern cosmology. One of the most important ingredients in our model of the universe has never been seen directly. No telescope has photographed it. No laboratory has captured it. Yet its presence appears woven throughout cosmic structure. We call it dark matter. According to current measurements, dark matter accounts for roughly 27% of the universe's total mass and energy content. Ordinary matter, everything from stars and planets to people and oceans, represents only a small fraction of the whole. The evidence is substantial. Galaxies rotate too quickly to be held together by visible matter alone. Galaxy clusters contain more gravity than their luminous contents can explain. Light from distant objects bends around invisible concentrations of mass through a phenomenon called gravitational lensing, where gravity acts like a cosmic magnifying glass. Dark matter solves these puzzles remarkably well. For decades, computer simulations based on the lambda cold dark matter model produced detailed predictions about how this invisible material should behave. One expectation concerns the centers of galaxies. Simulations indicate dark matter should pile up densely toward the middle, creating a steep concentration known as a cusp. The mathematics is clear, but observations continue pointing elsewhere. When astronomers examine dwarf galaxies, small systems strongly influenced by dark matter, they frequently find central regions that appear much smoother and more diffuse. Instead of cusps, they display broad distributions called cores. This discrepancy has a name. Researchers refer to it as the cusp-core problem. The issue has existed for many years, but observations from the James Webb Space Telescope are extending measurements to smaller and earlier galaxies, making the disagreement harder to dismiss. Another challenge appears nearby. The same simulations predict that the Milky Way should be surrounded by hundreds of small satellite galaxies, yet astronomers observe far fewer than expected. This mismatch became known as the missing satellites problem. The pattern keeps repeating. Within some distant galaxies observed by Webb, the arrangement of stars and gas does not align neatly with where simulations suggest dark matter concentrations should reside. The gravitational framework appears more complicated than anticipated. Possible explanations remain under active investigation. One idea proposes that dark matter particles interact with one another through forces beyond gravity. This concept, known as self-interacting dark matter, could naturally spread material outward and create the flatter core structures that astronomers observe. Other researchers explore different possibilities. A minority continue examining modified Newtonian dynamics, commonly called MOND. Rather than introducing invisible matter, this framework modifies gravity itself under extremely weak accelerations. MOND faces serious difficulties when applied to the largest cosmic scales, yet some galactic observations match its predictions surprisingly well. No consensus has emerged. Dark matter remains one of the strongest concepts in modern physics, supported by multiple independent lines of evidence, yet the details of its behavior increasingly resist simple explanations. Webb has not overturned the existence of dark matter. Instead, it is revealing a deeper truth. The invisible scaffolding underlying galaxies may be far more complex than the version we originally imagined, and every new observation adds another layer to a mystery that remains unfinished. A discovery made from dying stars altered the course of cosmology. In the late 1990s, astronomers studying distant supernovae expected to measure a universe gradually slowing under gravity's influence. Instead, the data revealed something profoundly different. The expansion was accelerating. Two independent research teams, the Supernova Cosmology Project and the High Z Supernova Search Team, reached the same conclusion in 1998. Galaxies were drifting apart faster as time passed. The farther astronomers looked, the clearer the pattern became. Something was pushing space outward. To explain this behavior, cosmologists introduced dark energy, a name given to the unknown cause behind cosmic acceleration. We cannot see it directly. We cannot isolate it in a laboratory. Yet its effects appear across the largest scales imaginable. Within the standard cosmological framework, dark energy takes a specific form. It is represented by the cosmological constant, an idea originally introduced by Albert Einstein and later revived for modern cosmology. The constant is assigned the Greek letter lambda. In practical terms, it means the energy density of empty space remains fixed forever. The assumption is remarkably simple. Wherever you travel in the observable universe, and whenever you measure it across cosmic history, dark energy should possess the same strength. This constancy became one of the foundation stones supporting the modern model. But foundations attract scrutiny. In 2024, the Dark Energy Spectroscopic Instrument, known as DESI, released one of the most ambitious cosmological datasets ever assembled. By mapping approximately 6 million galaxies across nearly 11 billion years of cosmic history, researchers created an extraordinarily detailed picture of how cosmic expansion evolved through time. The early results drew immediate attention. When DESI data was combined with other astronomical measurements, a subtle pattern emerged. The observations hinted that dark energy may not be perfectly constant after all. Instead, Its influence may have been stronger in the distant past and gradually weakened as the universe aged. This possibility has a name. Physicists call it quintessence, a dynamic form of dark energy that changes over time rather than remaining fixed. The concept has existed in theoretical studies for decades, yet observational support remained elusive. Until now, perhaps. The statistical significance currently falls between roughly 2.5 and 3 sigma. In scientific terms, sigma measures confidence in a result. 5 sigma is generally required before researchers declare a discovery. DESI has not crossed that threshold, yet the signal refuses dismissal. If future observations strengthen this trend, the consequences become difficult to overstate. The cosmological constant would no longer describe reality accurately. One of the central assumptions underlying modern cosmology would require revision. The implications extend far beyond equations. A changing dark energy alters predictions for the universe's ultimate future. Expansion might gradually slow. Gravity could eventually regain dominance. Some models allow repeated cycles of growth and collapse. Others predict more complex cosmic histories still. Everything depends on the answer. The fate of galaxies, stars, planets, and every atom you have ever known is tied to whatever dark energy truly is. At this moment, despite decades of study and increasingly powerful instruments, we remain confronted by the same essential fact. We still do not know. Some mysteries begin with uncertainty. This one begins with certainty. We know black holes exist. Their influence shapes galaxies, bends light across interstellar distances, and sends gravitational waves rolling through space when they collide. In 2019, the Event Horizon Telescope even revealed the shadow of one against glowing material spiraling inward. Yet certainty ends at a boundary. That boundary is called the event horizon, the surface beyond which no signal can return. Once matter crosses it, every possible path through spacetime leads deeper inward. You could imagine standing at that threshold, watching the last information from the outside universe fade behind you. Then our maps disappear. According to general relativity, Einstein's theory describing gravity as the curvature of spacetime, everything falling inward continues toward a singularity. A singularity is a point where density becomes infinite and the equations themselves stop producing meaningful results. Mathematics does not describe what exists there. Instead, it signals that something essential is missing. This distinction matters. Physicists generally do not regard singularities as real objects waiting to be discovered. They are warnings. They tell us that a successful theory has been stretched beyond the conditions where it can operate reliably. The equations reach a wall, but another framework reaches a different conclusion. Quantum mechanics, the theory governing particles and forces at microscopic scales, insists that information cannot simply vanish. Every physical system evolves according to rules that preserve its underlying information, even when that information becomes extraordinarily difficult to recover. Inside a black hole, those principles collide. If a star, planet, or cloud of gas falls inward and ultimately reaches a singularity, the details of its original state appear lost forever. Mass remains, gravity remains, but the information describing what entered seems erased from existence. That possibility troubled physicists deeply. In 1976, Stephen Hawking demonstrated that black holes are not completely black. Through quantum effects occurring near the event horizon, They should emit a faint glow, now known as Hawking radiation. Over immense stretches of time, this radiation gradually removes energy from the black hole until it eventually evaporates. The idea transformed black hole physics. Yet Hawking radiation appears thermal, meaning it carries little information about whatever originally fell inside. If the black hole disappears completely, where does that information go? Quantum mechanics says it must survive. General relativity offers no clear mechanism. The disagreement remains unresolved. Several proposals attempt to bridge the gap. Some suggest information is encoded on the event horizon itself. Others propose exotic quantum structures hidden within spacetime. A few models eliminate singularities entirely, replacing them with new physical states governed by quantum gravity. But no answer has achieved consensus. What lies beyond the event horizon remains inaccessible to direct observation. Every black hole, therefore, marks the meeting place of humanity's two greatest theories and the point where they cease cooperating. Somewhere beyond that boundary, gravity and quantum mechanics must become part of a deeper framework. We know the boundary exists. We know matter crosses it. Beyond that, the trail vanishes into territory where modern physics can no longer guide us with confidence. Imagine beginning with a map and discovering that the map itself has limits. No matter how powerful our telescopes become, no matter how long we observe, there exists a boundary beyond which information can never arrive. This is not a technological problem. It is woven into the structure of reality. We call this boundary the observable universe. Everything you have seen in this journey, every galaxy, black hole, gravitational wave, and atmospheric signature, exists inside a sphere roughly 93 billion light years across. That vast region contains hundreds of billions of galaxies and uncountable stars. Yet it is only the portion from which light has had enough time to reach us since cosmic history began. The boundary is not a wall. No barrier surrounds the observable universe. No curtain hangs at its edge. Instead, the horizon exists because light travels at a finite speed and the universe has a finite age. Beyond a certain distance, signals simply have not had sufficient time to arrive. But expansion changes the picture further. Space itself continues stretching while light travels through it. As a result, some regions are receding so rapidly that their light can never overcome the growing distance between us. The galaxies remain real. Their stars continue shining, yet the information they produce is forever inaccessible. Those regions are lost to observation. This consequence emerges naturally from modern cosmology. The horizon marks the limit of what can influence us and what we can influence in return. Beyond it lies territory permanently disconnected from our experience. The scale is difficult to grasp. Inflationary theory, the leading explanation for the universe's earliest moments, proposes that a tremendous burst of expansion occurred fractions of a second after the Big Bang. According to many versions of that theory, the entire universe extends vastly beyond the observable portion, perhaps unimaginably beyond. Some calculations suggest the total cosmos may be so much larger that comparing it to the observable universe resembles comparing an ocean to a single droplet. In certain inflationary models, distant regions may even possess different values for fundamental physical constants. That possibility carries profound implications. Gravity, electromagnetism, and the nuclear forces govern everything we observe. They determine how stars ignite, how atoms form, and how galaxies evolve. Yet if those constants vary elsewhere, then the laws we regard as universal may describe only our local cosmic neighborhood. A question naturally follows. How representative is our sample? Every anomaly explored in recent years, from unexpected galaxies to puzzling expansion measurements, comes from observations within this limited horizon. We are attempting to understand the totality of existence using information drawn from a remarkably small, accessible region. But that limitation does not diminish the achievement. From one planet orbiting an ordinary star, we have reconstructed billions of years of cosmic history and uncovered patterns spanning unimaginable distances. Still, every discovery occurs through a narrow observational window, and as that window grows clearer, the universe beyond it appears not simpler, but increasingly vast, layered, and surprising. Some ideas enter science through observation. Others emerge from equations that refuse to stay confined. The multiverse belongs to the second category. It was not invented to solve a mystery about distant galaxies or explain an unexpected telescope image. Instead, it appeared independently within several major frameworks of modern physics, each following its own mathematical path. That coincidence attracts attention. One route begins with inflation, the brief era of extraordinary expansion thought to have occurred fractions of a second after the Big Bang. Inflation explains why the observable universe appears remarkably smooth across immense distances. It also matches important features measured in the cosmic microwave background. But some versions go further. In eternal inflation, the process never completely ends. While inflation stops in one region and produces a universe like ours, it continues elsewhere. New regions keep forming indefinitely. Each becomes a separate cosmic domain, isolated by distances so vast that communication between them is impossible. The process never concludes. A second path emerges from quantum mechanics. In 1957, physicist Hugh Everett proposed the many worlds interpretation. Instead of a quantum event selecting one outcome from many possibilities, every outcome occurs. Reality branches. Each branch contains a different version of events, evolving independently after the split. The implications are difficult to visualize. Every particle interaction, every measurement, every microscopic uncertainty contributes to an ever growing collection of parallel histories. Within this framework, alternative versions of reality are not possibilities. They are physical outcomes existing simultaneously in separate branches. Then comes string theory. String theory attempts to unite gravity with quantum mechanics by describing fundamental particles as tiny vibrating strings, yet the mathematics permits an enormous number of stable configurations. Researchers call this collection the landscape. Its scale is staggering. Current estimates suggest roughly 10 to the power of 500 possible vacuum states, each corresponding to different physical laws or constants. If all these possibilities exist somewhere, then reality may contain an immense ensemble of universes with profoundly different properties. The controversy is not primarily mathematical. Many physicists agree these frameworks possess internal consistency. The debate centers on testability. Can a theory be considered science if direct observation remains permanently inaccessible? The question reaches beyond cosmology and into the philosophy of knowledge itself, but researchers continue searching for clues. One proposed test involves collisions between neighboring universes during the inflationary era. Such encounters could leave subtle scars in the cosmic microwave background, the ancient radiation released when the universe first became transparent. Certain anomalies have drawn attention. The cold spot and the hemispherical asymmetry discussed earlier display features some researchers consider broadly compatible with these collision scenarios. Compatibility, however, is not confirmation. Alternative explanations remain viable, and no observation has yet established the existence of another universe. That uncertainty defines the subject. The multiverse stands at a remarkable boundary where theoretical physics encounters the limits of observation. Here, increasingly powerful instruments do not necessarily produce simpler answers. Instead, they illuminate how much of reality may exist beyond direct reach, leaving us to examine the consequences of ideas that mathematics permits but evidence has not yet fully claimed. Imagine adjusting the universe the way you might tune a single note on an instrument. Change it slightly, almost imperceptibly, and the entire performance becomes something else. Across modern physics, researchers have discovered that many of the numbers governing reality appear to occupy an extraordinarily narrow range, one that allows stars, planets, chemistry, and ultimately observers like us to exist. These numbers are called physical constants. They include the strength of gravity, the mass of the electron, the strength of the strong nuclear force that binds atomic nuclei together, and the value associated with dark energy. We do not currently know why these constants possess the values they do. We can measure them with remarkable precision. Explaining them remains far more difficult. Consider gravity first. If gravity were only modestly stronger, stars would burn through their nuclear fuel far more rapidly. Their lifetimes could shrink from billions of years to mere thousands. Planetary systems would struggle to develop stable environments before stellar evolution transformed them. The long biological timescales required for complexity would become difficult to imagine. Shift the value in the opposite direction. Matter would resist gathering into dense structures. Vast clouds of hydrogen could drift through cosmic history without ever collapsing into stars. Galaxies would be sparse. Heavy elements would remain largely uncreated. The universe would be darker and chemically simpler. Yet gravity is only one parameter. The cosmological constant presents an even deeper puzzle. This quantity describes the energy density of empty space itself. Observations indicate a value that permits galaxies to form and remain gravitationally bound. But quantum field theory, our most successful framework for describing subatomic particles, predicts a value larger by roughly 10 to the power of 120. The mismatch is astonishing. No other disagreement between theory and observation approaches this scale. Physicists often describe it as the worst prediction in science, not because the theory lacks success elsewhere, but because the discrepancy is so enormous that ordinary intuition becomes useless. From this tension emerges the fine-tuning problem. Why do these constants possess values compatible with complexity? Why not different values that produce a sterile universe? Two broad categories of explanation dominate the discussion. The first points toward the multiverse. If countless universes exist with different physical constants, then observers naturally find themselves in regions where conditions permit their existence. This reasoning is known as the anthropic principle, the idea that our observations are influenced by the fact that we are here to make them. But another possibility remains. The constants may not be arbitrary at all. Somewhere beneath our current theories could lie a deeper framework from which every value follows inevitably. In that picture, the universe looks finely tuned only because we have not yet uncovered the underlying rules. Recent measurements add another layer. Hints from the dark energy spectroscopic instrument suggest dark energy may evolve over time rather than remain fixed. If that trend survives future scrutiny, some multiverse models gain additional flexibility. Yet the evidence remains preliminary, and competing explanations continue to be explored. So we find ourselves in a familiar position. The numbers governing reality appear remarkably special. We can measure them, we can debate their meaning. But the reason they possess these particular values remains one of the deepest unanswered questions in all of physics. Few scientific achievements have survived scrutiny as successfully as the two great frameworks that govern modern physics. One describes the universe on the largest scales, the other governs the smallest. Together they explain black holes, atoms, stars, chemistry, electronics, and much of the observable cosmos. Yet when we attempt to place them side by side, the harmony breaks. We begin with gravity. In 1915, Albert Einstein introduced general relativity, a theory describing gravity as the curvature of spacetime itself. Matter tells spacetime how to bend. Spacetime tells matter how to move. Over more than a century, every major test has strengthened confidence in its predictions. Light bends around massive objects exactly as expected. Binary pulsars lose energy at the predicted rate. Gravitational waves arrive carrying signatures that match Einstein's equations with astonishing precision. The success is remarkable. At the opposite end of reality stands quantum mechanics. Developed through the 1920s and later expanded into quantum field theory, it governs particles, forces, and the microscopic structure of matter. Every modern computer chip, every laser, every nuclear reaction, and every chemical bond depends upon its accuracy. Experimental confirmations have reached better than 1 part in a trillion. Yet the two frameworks speak different mathematical languages. When physicists attempt to apply quantum rules to gravity, the calculations produce infinities that cannot be removed consistently. The equations stop delivering meaningful answers. This failure is known as non-renormalizability, meaning the mathematics cannot be cleaned up into a physically sensible theory. For nearly a century, researchers have searched for a path beyond that barrier. One candidate has dominated much of that effort. String theory proposes that fundamental particles are not dimensionless points, but tiny, vibrating strings of energy. Different vibration patterns appear as different particles. In this framework, gravity emerges naturally alongside the other known forces. The idea is elegant. It is also demanding. The mathematics requires additional spatial dimensions curled into scales far beyond direct observation. The challenge remains significant. Despite decades of development, no observation has yet confirmed a prediction unique to string theory. The framework remains mathematically rich, but experimental support has not arrived. Another path follows a different intuition. Loop quantum gravity suggests spacetime itself is granular. Instead of a smooth continuum, reality may consist of tiny discrete units woven into an underlying network. At scales approaching the Planck length, approximately 10 to the power of negative 35 meters, the familiar concept of continuous space could dissolve into something more fundamental. Direct measurements remain impossible, but nature occasionally provides indirect opportunities. Photons, particles of light, travel across billions of light years before reaching our instruments. If spacetime possesses hidden quantum structure, tiny effects could accumulate during those immense journeys. Subtle distortions in the energy spectra of distant cosmic sources may preserve clues from realms far beyond laboratory reach. That possibility gives extraordinary value to modern observatories. As we gather light from the earliest galaxies and most distant explosions, we are doing more than mapping the cosmos. We are testing the foundations beneath every physical law we know. Somewhere beyond our current equations may exist a deeper framework from which gravity, quantum mechanics, space, time, and matter all emerge together. For now, that theory remains unwritten, waiting beyond the edge of our understanding. After moving through contradictions, tensions, and unanswered questions, it is worth pausing beside something equally important. Scientific progress is not measured only by mysteries discovered. It is also measured by knowledge secured. As remarkable as the anomalies have been, the James Webb Space Telescope has already transformed humanity's understanding of the cosmos in ways that are both confirmed and profound. Its reach alone changed astronomy. For the first time, we have directly observed galaxies from roughly 290 million years after the Big Bang. When you look at those observations, you are seeing light emitted before Earth existed, before the Sun formed, before our galaxy completed many of its earliest chapters. No previous instrument had carried human vision so close to the beginning. That achievement opened a new window. One of Webb's major successes has been clarifying reionization, the era when the first generations of stars altered the universe itself. Early hydrogen gas absorbed light efficiently, making space difficult for radiation to cross. As the first stars ignited, their intense ultraviolet energy stripped electrons from hydrogen atoms. Reionization, meaning the restoration of electrically charged particles, gradually transformed the cosmos into a place where light could travel much more freely. Now we can watch traces of that transition directly. Spectroscopic analysis, the study of how matter absorbs and emits specific wavelengths of light, has revealed the fingerprints of this process across distant galaxies. What once existed primarily in theoretical models is increasingly visible in observational data. But the surprises extend beyond that milestone. Galaxy formation appears far richer than expected. Researchers anticipated immature structures dominating the first billion years. Instead, Webb has revealed disks, elongated systems, compact spheroids, and surprisingly organized arrangements appearing much earlier than many simulations suggested. The early universe seems capable of producing variety at remarkable speed. Large-scale structure has become clearer as well. The cosmic web, the immense network of filaments connecting galaxies across space, was predicted decades ago through theoretical calculations and computer simulations. Webb has helped provide direct views of portions of that architecture, revealing matter distributed along vast threads spanning hundreds of millions of light years. The universe is not randomly arranged. It possesses structure on breathtaking scales. Chemical history has also come into sharper focus. Observations now allow astronomers to trace the accumulation of carbon, oxygen, silicon, and iron through cosmic time. We can follow how successive generations of stars enriched galaxies, gradually creating the ingredients needed for rocky planets and complex chemistry. In a sense, we are watching the periodic table assemble itself across billions of years. Closer to home, another revolution is unfolding. Exoplanet research has moved beyond simple detection. Webb can analyze atmospheres, identifying molecules suspended above distant worlds. What was once limited to a small number of giant planets is becoming a systematic exploration of diverse planetary environments, including some that may possess conditions favorable for liquid water. The telescope itself continues exceeding expectations, operating at temperatures near 233 degrees below 0 Celsius. Its mirrors remain extraordinarily stable, and fuel consumption has been so efficient that mission planners estimate a lifespan potentially extending beyond 20 years. Every observation adds another piece. Each photon collected began its journey long before humanity existed. After traveling across immense stretches of time and space, it arrives carrying information no person has ever possessed before. That alone represents one of the greatest expansions of knowledge in human history. Scientific revolutions rarely begin with grand announcements. More often, they start with a researcher staring at a result that refuses to behave. A calculation is checked again. A dataset is processed one more time. Alternative explanations are tested. Hours become days. Confidence grows reluctantly. The numbers remain unchanged. That pattern has appeared repeatedly during the James Webb Space Telescope era. As the first deep field observations arrived in 2022, astronomers expected refinements to established ideas. Instead, some researchers found themselves confronting galaxies that appeared larger, brighter, and more developed than prevailing models anticipated. The surprise was not theatrical, it was technical. Yet the reaction from specialists revealed how seriously the results were being taken. Alison Kirkpatrick of the University of Kansas expressed that reaction with unusual candor. After examining the emerging observations, she told journalists she had a sinking feeling that the field might possess the wrong picture of the universe. The statement spread widely, not because it was dramatic, but because it reflected genuine professional uncertainty from someone trained to evaluate astronomical evidence carefully. Others experienced a similar moment. Ivo Labe and his collaborators encountered massive early galaxies whose existence challenged expectations built over decades. Before publishing, researchers repeated analyses, tested assumptions, and scrutinized possible errors. The objects remained. Their paper introduced the phrase universe breakers, terminology chosen in a peer-reviewed scientific publication. Such language is rare. Scientists generally avoid it unless they believe a discrepancy deserves serious attention. The concern extended beyond individual discoveries. Mike Boylan Colchin at the University of Texas drew upon an engineering concept known as stress testing. In engineering, a structure is pushed toward its limits to reveal hidden weaknesses. Applied to cosmology, the phrase carried a specific meaning. New observations were exposing areas where foundational predictions appeared increasingly strained. But scientific concern differs from public anxiety in important ways. Researchers are not worried that reality itself is unstable. They are examining whether particular mathematical descriptions remain adequate when confronted with increasingly precise measurements. The distinction matters. The universe is doing what it does regardless of human expectations. The question is whether our models describe that behavior completely. History offers many examples. Mercury's orbit challenged classical gravity before general relativity resolved the discrepancy. Ultraviolet radiation puzzles helped launch quantum theory. Small inconsistencies sometimes become pathways to deeper understanding. Most disappear after additional investigation. A few change everything. That is why collaboration papers are written so carefully. When the Dark Energy Spectroscopic Instrument released results in 2024, suggesting dark energy might evolve over time, the language remained measured, yet the implication was clear. If future observations strengthen the signal, substantial revisions to the standard cosmological framework may become necessary. A single anomaly can often be absorbed. Several independent anomalies, pointing toward related weaknesses, are harder to dismiss. When separate observations, different instruments, and unrelated research groups begin identifying tensions in similar regions of theory, attention naturally follows. What keeps scientists returning to these puzzles is not fear, it is discipline. The willingness to follow evidence wherever it leads remains one of the defining strengths of science. Sometimes that process confirms long held ideas, sometimes it reveals their limits. The restlessness described by many researchers emerges from recognizing that possibility and refusing to look away from it. Look beyond the James Webb Space Telescope for a moment, and you begin to see something larger taking shape. Across Earth and space, a new generation of observatories is coming online at nearly the same time. Each was designed to answer different questions. Together, they form a coordinated effort to examine the deepest puzzles we have explored throughout this journey. The timing is extraordinary. For decades, cosmologists often waited years between major advances in observational capability. Now, multiple instruments are arriving within a single scientific generation. Data that once seemed impossibly distant is about to become routine. Among the most ambitious is the European Space Agency's Euclid mission, launched in July of 2023. Its purpose is straightforward in principle, though immense in execution. Euclid is mapping the positions and shapes of billions of galaxies across roughly one-third of the sky, creating a three-dimensional portrait of cosmic structure stretching across billions of years. The target is dark energy. By measuring how galaxies cluster and evolve through time, Euclid aims to determine whether the force driving cosmic expansion behaves exactly as current models predict. Early results released in 2024 demonstrated performance exceeding many expectations, but some large-scale patterns already appear intriguing enough to warrant deeper investigation. Meanwhile, another observatory is preparing to watch the sky continuously. The Vera Rubin Observatory in Chile will survey the southern heavens repeatedly over a 10-year campaign. Rather than taking isolated snapshots, it will build a living record of change. Billions of galaxies will be cataloged. Millions of supernovae will be detected. Asteroids, variable stars, and transient phenomena will emerge from an observational archive unlike anything previously assembled. Nothing comparable has existed. The Nancy Grace Roman Space Telescope, expected to launch in 2027, will complement both Webb and Euclid. Operating in infrared wavelengths, Roman will conduct vast surveys designed to trace the expansion history of the universe with exceptional precision. Because the Hubble tension remains unresolved, Roman's measurements may become some of the most important cosmological data ever collected. But gravity itself is also entering a new era. The Laser Interferometer Space Antenna, known as LISA, is planned for the next decade. Three spacecraft separated by approximately 2.5 million kilometers will function as a gigantic gravitational wave detector in space. Unlike current observatories, LISA will sense lower frequency signals generated by mergers involving supermassive black holes throughout the observable universe. The scale is staggering. Ground-based successors are advancing as well. Projects such as the Einstein Telescope and Cosmic Explorer are expected to improve gravitational wave sensitivity by factors ranging from 10 to 100. Events currently invisible may become commonplace observations. Taken individually, each instrument is powerful. Taken together, they represent something unprecedented. Independent measurements will test the same cosmic questions from multiple directions. Dark matter, dark energy, galaxy formation, gravitational waves, and the expansion history of the universe will all face scrutiny at levels never before possible. But the most important outcome is not tied to any single answer. If the apparent contradictions dissolve, the standard model will emerge stronger. If they persist, new physics will move from speculation toward necessity. Either way, Many of the questions keeping researchers awake today may finally encounter evidence capable of deciding them. The next decade will not merely add information, it will reveal whether our current picture of the cosmos is fundamentally complete or only the beginning of a much larger story. A photograph can sometimes change the scale of a thought. In 1990, far beyond the outer planets, the spacecraft Voyager 1 received an unusual instruction. At the request of Carl Sagan, NASA commanded the probe to turn its camera back toward home. From a distance of roughly 6 billion kilometers, the planets were almost impossible to distinguish. Earth appeared as a tiny speck, less than a pixel wide, suspended within a streak of scattered sunlight. That image became famous, not because it revealed something new about Earth itself, but because it revealed how small our familiar world becomes when viewed from far enough away. Borders vanished, nations disappeared. Entire histories compressed into a point of light that could barely be seen. Now, place that perspective beside what the James Webb Space Telescope is showing us. When you look into one of Webb's deep field images, almost every visible point is not a star, it is a galaxy. Each galaxy may contain hundreds of billions of stars. Around many of those stars, planets almost certainly orbit. Some are young, others formed when the universe was still in its earliest chapters. The numbers resist intuition. One celebrated Webb deep field covers a patch of sky roughly equivalent to a grain of sand held at arm's length. Yet within that tiny region, the image is crowded with galaxies stretching across vast spans of cosmic history. The apparent emptiness between familiar stars dissolves into structure. Everywhere we look, there is more. But scale alone is not the most remarkable part of this story. What truly stands out is the unlikely path that brought us here. A species that once painted animals on cave walls, approximately 40,000 years ago, now builds instruments capable of examining the chemistry of distant worlds. The progression feels almost impossible. Webb has detected molecules in atmospheres surrounding planets more than 100 light-years away. It has measured ancient starlight that began its journey billions of years before Earth existed. It has identified galaxies whose light departed when the cosmos was still young enough to challenge current models of formation and growth. Consider the star commonly known as Methuselah. Located about 190 light-years from Earth, it appears to have formed astonishingly early in cosmic history. Long before our planet emerged, its light was already crossing space. Then there is the distant galaxy known as JADES-GS-Z 14-0. The light-reaching Webb from that system began traveling approximately 13.5 billion years ago. At that time, there was no Earth, no sun, and no human observer waiting to receive it. Yet the signal arrived. It reached a mirror, assembled by descendants of microscopic organisms that did not exist when the journey began. That fact sits beneath every anomaly we have explored. The reason certain discoveries trouble cosmologists is inseparable from the achievement itself. We have become precise enough to recognize when reality differs from expectation. And in that recognition, the pale blue dot gains a new meaning. We remain small within the cosmos, but we are no longer looking outward blindly. We have learned enough to notice the universe answering back. Scientific revolutions rarely begin with certainty. They begin with a mismatch. A measurement refuses to agree with a prediction. A telescope sees something unexpected. An equation that seemed complete develops a crack. At first, the discrepancy appears small, almost forgettable. Yet history shows that some of the deepest changes in human understanding emerged from exactly those moments. We have seen this before. For much of the 20th century, Many astronomers favored the steady state universe, a model proposing that the cosmos was eternal and broadly unchanging. Then came the discovery of the cosmic microwave background, the faint afterglow of the early universe. The evidence accumulated, the model yielded, the Big Bang became the new framework. Later, another expectation failed. Gravity was supposed to slow cosmic expansion over time. Observations of distant supernovae during the late 1990s revealed the opposite. Expansion was accelerating. An entirely new ingredient, dark energy, entered cosmology. The picture changed again. Now we find ourselves standing in a familiar position. The James Webb Space Telescope did not arrive to overturn established ideas. It was built to investigate them in greater detail. Yet some of its observations have exposed tensions that refuse to disappear. Early galaxies appear surprisingly mature. Large-scale structures stretch farther than expected. Measurements of expansion remain difficult to reconcile. Hints emerge that even dark energy may be more complicated than assumed. Any one of these findings might eventually find a conventional explanation. But patterns matter. When several independent observations begin pointing toward related weaknesses, researchers pay attention, not because a crisis is guaranteed, but because nature may be revealing a deeper layer beneath the current model. The remarkable fact is how much remains unresolved. Dark matter and dark energy together account for approximately 95% of the universe's mass and energy content. Yet, their fundamental nature remains unknown. We measure their effects with impressive precision. We still do not know what either one actually is. Other questions remain equally open. We do not know whether the universe extends forever or possesses a finite size beyond our horizon. We do not know whether physical laws remain identical in regions forever inaccessible to observation. We do not know whether life has appeared elsewhere, despite discovering worlds by the thousands. Even the foundations contain uncertainty. Inside a black hole, established theories cease agreeing with one another. At the beginning of cosmic history, our equations approach conditions they cannot fully describe. The earliest fractions of a second remain partly hidden behind mathematics that is still incomplete. You might expect such admissions to feel discouraging. Instead, they reveal something valuable. Science is often imagined as a collection of answers. In practice, it is also a discipline of identifying the right questions. Progress depends on recognizing where knowledge ends and evidence must take over. Every major discovery began with a willingness to acknowledge uncertainty rather than conceal it. That is why these unknowns matter. They are not failures of cosmology. They are signposts. They mark the places where observation has reached the edge of explanation, where curiosity remains larger than certainty, and where the next understanding will eventually emerge. It begins with looking upward. Across every known human civilization, the same gesture has repeated itself. Eyes lifted toward patterns of light, hands tracing meaning onto darkness. Long before instruments existed, the sky already served as a shared reference point for thought. It connected distant cultures without ever speaking a word. The stars above Mesopotamian scribes 5,000 years ago are still there today. Their photons continue to travel, reaching modern telescopes with the same patience they carried at the moment of emission. What changes is not the sky itself, but the depth of our interpretation. But what feels new is not the sky, it is us. The questions have remained remarkably stable across time. What exists beyond Earth? Whether we are alone, how the universe began its unfolding, These inquiries appear ancient, yet they are now being approached with tools that redefine what it means to ask. The James Webb Space Telescope stands within that lineage, not as a replacement for curiosity, but as its amplification. Its construction required decades of engineering, international coordination, and sustained scientific commitment measured in billions of dollars and years of precision work. All of it to extend a single human capability, the ability to see further back in time. Science, in this sense, is not a collection of discoveries. It is a continuous exchange between generations. One era builds the instruments, the next inherits the data. Each step refines what the previous one could only approximate. JWST now occupies a central position in that exchange. It delivers results that expand expectation and sometimes disturb equilibrium. Early galaxies appear more structured than models anticipated. Cosmic timelines compress in unexpected ways. Chemical complexity emerges earlier than previously assumed possible. Each observation adds texture to a picture that was once smoother and simpler. But complexity is not failure, it is instruction. Every mismatch between prediction and measurement signals a place where understanding is incomplete. The universe does not resist explanation, it simply exceeds it. Each anomaly becomes a coordinate pointing toward refinement rather than collapse. The engineers who designed JWST anticipated this. They did not build it to confirm certainty, they built it to challenge it. That intention is embedded in every mirror segment and every calibration sequence. What follows from that design is a kind of disciplined uncertainty. Researchers, studying its data, describe not panic but attentiveness, a heightened awareness that something important is not yet fully accounted for. That awareness is not discomfort in the emotional sense. It is the professional recognition that precision is still evolving. Across 5,000 years, the questions have not changed. Only the clarity of the answers has shifted. We now possess instruments capable of detecting galaxies from the earliest epochs of cosmic history, measuring atmospheric chemistry on distant worlds, and reconstructing the universe's expansion with unprecedented resolution. Each capability brings us closer to hearing what the cosmos is actually saying. And for the first time, that conversation is beginning to return structured responses. Not simple ones, not final ones, but intelligible ones. We are no longer only asking into the night sky. We are beginning to listen. Night on Earth feels like a pause, but it is not. Above the atmosphere, nothing pauses at all. The universe continues its expansion, its collisions, its slow gravitational choreography across scales that dwarf any human sense of duration. Galaxies pass through each other over hundreds of millions of years, their shapes stretching and folding like ink in water. A single human lifetime is too brief to register even the beginning of such change. But the sky never waited for us. Neutron stars keep rotating in the spaces between galaxies, some spinning hundreds of times each second. Their magnetic fields sweep beams of radiation outward, like lighthouses built without an ocean to illuminate. Those signals travel through darkness that has no edge we can reach, no boundary we can approach, no wall to mark its end. Somewhere within that expanse, a world like K218b continues its orbit around a faint red star. Light touches its atmosphere, passes through gases we are only beginning to measure, and carries chemical traces across interstellar distances. Whether that world hosts anything that perceives its own sky remains unanswered, but it is no longer unthinkable to ask. Far beyond even that, Space stretches into regions we will never observe directly. The observable universe itself may be only a fragment of a far larger whole, reduced to something like a single grain of sand within an endless shore. The horizon we see is not an edge, it is a limit defined by time and expansion. Every photon that reaches us carries a history longer than Earth itself. The light captured by the James Webb Space Telescope tonight began its journey in epochs when no planets had yet formed around our Sunday. It traveled for billions of years through an expanding cosmos before striking a mirror cooled to nearly 233 degrees below 0 Celsius. There, it is transformed into streams of data that humans interpret with patience and care. Some of those interpretations will reinforce existing models, others will resist them. But resistance is where understanding begins to deepen. When measurements do not align, when predictions fail in precise and repeatable ways, the discomfort that follows is not confusion alone. It is recognition that the map is incomplete. That feeling has appeared before in science, always before a shift in perspective. It does not signal collapse, it signals contact. The universe has existed for approximately 13.8 billion years. It operated long before observers arrived, and it will continue long after the last instruments fall silent. In comparison, human observation is brief, fragile, recently arrived, and yet, within that brief window, something extraordinary has happened. We have built instruments capable of receiving light that predates Earth. We have learned to read the composition of distant atmospheres, to trace the structure of galaxies across cosmic time, to measure the expansion of space itself. We have begun to ask questions that the universe can answer in return. That exchange is still unfolding. But the most important part is not the answers themselves. It is the fact that the answers exist and that they keep arriving in forms we did not expect. To look deeper into the universe is not to step away from certainty. It is to discover that certainty was never the destination. It was always the beginning of the next question.